Okay, let's go ahead and get started. My apologies to those of you that were here earlier. I've already told them this, but over the years, I have found that if I write the exam such that the average is 75%, then I get the right number of A's in the class, the right number of B's in the class, and so forth. So I have really tried to write my exam so that the average is 75%, and I've gotten really good at it at Montana State University. I used to be able to just peg it right at 75, and let's be clear, I can write an exam that has an average of 30 on it. I did that a lot when I was brand new teacher. That's not something to be proud of. I'd go to garage sales and someone would say, "Oh, I had you as a professor." I said, "When?" I said, "Oh, back in '92." And I said, "Oh, I'm so sorry," because that's when the averages were very low. So what I'm saying is that I misjudged you. Okay, I really thought that the average on this exam was going to be 75, and you nuked it out of the water. You've done good. And so I'm proud of you as a class. Now, having said that, some of us had a difficulty with this. And for those individuals, I have good news and bad news. The good news is that this exam only counts as 14% of your grade in the class. And so that means that if you say you got 50% on that exam, that would be a failing grade. That means you lost 7% in the overall course grade. But you can go all the way down to 90% before you lose your A. So fail that exam and still do well in the class. The bad news is that everything that comes after is built on that study of kinematics, of motion. And so you can't just dust yourself off and walk away from that exam and say, "Oh, well, that didn't go well." You're going to have to go back and figure out what you did wrong, what you misunderstood. Now, this afternoon, I'm going to sit down with that exam and work through each of the problems on a video recording, and I'll send you a link to that. And in that recording, I'm going to give some personal information, like my favorite color or my favorite pet. And so before you come to me in my office and ask to go through the questions step by step individually, I'm going to ask if you know what my favorite color is, so I can tell whether you took the time to watch the video to see the answers, because there's 665 students in this class, and going through the test question by question, 606, I don't have that many years left. I'm an old man. Okay. So the other good news is that if you failed this exam, your parents still love you. And so do I. Okay. So that's the big news. Would someone be willing to give us an opening prayer this morning? Anyone? Oh, good, sir.
Heavenly Father, we're very grateful for this day that we can be here at BOU campus, that we can learn about physics, and for Dr. Francis and for his hard work and preparation. Please bless us as we go throughout the remainder of our day, that we can remember thee and thy son Jesus Christ, that we can look for the one, and that we may be instruments in thy hands. We're grateful for the gospel, and we're grateful for our good friends and our families. Please bless them wherever they are, and we love thee and we say things. In the name of Jesus Christ, amen.
Thank you. Okay, today we are going to talk about one of the more difficult uh, topics in forces, and that is we're going to talk about friction. And so let's start, however, with a review of where we've been. Suppose I were to put a pop can on this table, and originally that was a Coke can, but this is BYU, so it's a Sprite can. If I asked you to draw a free body diagram for that can, what you would do is you'd first of all put the gravitational force. But of course, all forces have to be labeled by on. Every force, every macroscopic force is a dance between a pusher and a pushee. Something exerts the force and something feels the force. In this case, this would be the earth pulling on the can. I then asked, are there any magnets in this problem? No, not yet, they're coming. So what touches the can? The table. Well, does it push or does it pull? Not a string, not a thread, not a chain, not a rope. It pushes. Whenever one thing pushes on another, there will always be a normal force, by which I mean perpendicular. That would be a table on the can. There may also be a friction force. If you're wondering whether there is a friction force or not, reach down the table and ask if that changes anything. If the table's level, it doesn't change anything, so I don't need a friction force. That's the free body diagram. I know it's correct because I followed the recipe. Okay? Now these two forces are equal and opposite. By what law? Shout it out. Yeah, if you said third law, you just need to slap yourself silly, okay? Slap yourself silly. These have nothing, I repeat, nothing to do with Newton's third law. I can tell that because they're not the same flavor. One's a contact force, normal force. One's a non-contact force, gravitational force. They don't have the same indices, reverse, and they're acting on the same dot, on the same free body diagram. They have nothing to do with Newton's third law. Now, in your tutorial homework, what you were asked to do is essentially prove that those are not Newton's third law force pairs. And the way you do that is you change it up. For example, if I were to put that table and that can in an elevator with acceleration up, and let's just pause a moment. Is that elevator going up to the 10th floor or down to the lobby? We don't know. If it's going up to the 10th floor, it's speeding up. If it's going down to the lobby, it's slowing down. And both of those feel exactly the same. If you don't have windows in your elevator or buttons that light up, you don't know which it is, okay? What has to change in my free body diagram? This diagram now has to scream that acceleration. And I'm here to tell you people, you cannot change that force without diet or exercise, okay? That's just a hard rule. And so that means we have to change the normal force. It has to get bigger. So clearly, these are not third law companions. They're not equal to each other, okay? What is the third law companion to that normal force? What would it be? Right, normal force. If that's a normal force, this has to be a normal force. Instead of the table on the can on the table. What free body diagram would I find that on, good sir?
What's that?
What's that? Which free body diagram would I find this force on?
On the table.
On the table. It's always the last indices. See, this is on the can, on the can. This would be, oh, that sounds bad. I'm sorry. This is on the table. So I would put tick marks there to indicate that those are third law companions, always equal and opposite. Now, it turns out that every force has a third law companion. This gravitational force, Earth pulling on the can, has a force on the Earth, can on the Earth. It turns out that this particular free body diagram is not one that you want to draw, because there are billions and billions of forces on that diagram. But one of them will be the can pulling on the Earth, and those will be always equal and opposite. Now, as we talked about before, a lot of you came in. The Earth is pulling on this book just as hard as the book is pulling on the Earth, and so if this weighs 5 newtons, the Earth is pulling on it with 5 newtons of force, and it's pulling on the Earth with 5 newtons of force. But when I drop it, it races down. The Earth didn't race. You didn't feel the Earth race up, did you? And that's because that 5 newtons is enough to accelerate this little book, but you act on the Earth with 5 newtons. Well, I don't care. That's just, the Earth is too big to care about a 5 Newton force. Okay, does that make sense? Now, here's the big idea. Whenever you are comparing two forces that are on the same free body diagram, you do it with Newton's second law. And every time you invoke Newton's second law, you have to qualify your statement. I would say that normal force is larger than that gravitational force. By Newton's second law, finish your sentence with acceleration up. This diagram has to scream that acceleration up. Okay? Now, whenever you are comparing two forces that are on different free body diagrams that have the same flavor, the same indices reversed, you invoke Newton's third law and close your mouth. I have people on exam saying, oh, those are equal and opposite by Newton's third law because it's accelerating, or because it's not accelerating, or because it's Tuesday. No, if they're equal and opposite by third law, they're always equal and opposite by third law. You don't need to qualify that in any way whatsoever. Okay? Now, if we go back to the situation of zero acceleration, and that could either be stopped or constant velocity, these two are now equal and opposite, but they're equal and opposite by Newton's second law, finish your sentence, with zero acceleration. This diagram has to scream balance. I only have one force up, one force down. They have to be equal. Please check on your neighbor and see if that's what they got out of Tuesday's lecture.
I learned that on the. Right, when they're on their own. That makes sense.
Okay, we had a pretest last week, and in that pretest, we were asked to compare these two forces. The force by the snow on the crate to the force by the crate on the snow. Now you can almost hear those indices lift up and pirouette around and come back down. Okay, and that's an indication that those have to be third law companions, and so they are equal to each other. Okay, now there's still going to be a net force up on the crate. Okay, this force here is going to be bigger than the weight by the Earth on the crate, but these two forces are on different objects. They can't cancel each other. They're acting on different objects. So let's see if we understand where we've been. as a bungee jumper slows, let's say it correctly, as the bungee cord slows you down, the force of the cord on your ankles is greater than, equal to, or less than the force of your ankle on the cord. Let me get you started here. The first time always takes a little bit more. Now you can vote. Vote early, vote often.
What do you think?
Okay. Last call. Get your point. Okay. Whoa, that's really good. Okay. I'm
Yesterday.
a little bit worried about these folks, but they're equal to each other. And again, what we're comparing is the tension by the cord on the ankle to the tension by the ankles on the cord. They're the same flavor of force with the indices that are reversed. And so those are third law companions. They're equal by Newton's third law. Okay. Questions on that? Let's ask the second great question. As the bungee cord slows you down, the force of the cord on your ankles is greater than, equal to, or less than your weight. With your clicker.
So now it's gonna be great.
And folks, on these two questions, by all the law and the prophet.
Slowing down. I don't know.
Okay. Get your vote in.
Down.
Okay, there were 305 of us a second ago. Somebody hasn't voted. Too late. Okay, good job, everybody. Good job. In this case, we are looking at a situation where the velocity vector is down. Because we're slowing down, the acceleration vector is up, but we want to ignore the velocity and we want to make our force diagram scream the acceleration. And so that means I need to have more force up than I have down. And so that means the answer is greater than. And I would justify that answer with Newton's second law. Qualify it, finish your sentence with acceleration up. Does that make sense? Okay. So, pop quiz. Newton's third law does not apply if a system is accelerating. Is that true or false? Go ahead and use your clicker, please.
I think on the first. That's actually great. Your brain, man. Those are
Okay. Pop quiz means quick. Get her done. Okay, there we are. Oh, I'm sorry. Fault is not the right answer, people. The right answer is wave fault. Wave fault. Totally. Ah, icky poo. Icky poo. Okay, let's try this one. Newton's third law companion forces never act on the same object, true or false.
It's like blue on red and red on. Yeah, it's like.
Like the mutual ender.
Okay, three more of you, get it in.
That's what I'm glad.
Okay,
I mean, it's possible.
there we go. Good, that is true. One more question. Contact forces have third law companions, but gravitational forces do not. Folks, I would like for us all to get this correct so that we can say that once during the semester, we were in agreement.
Gravity. True last time to this.
Once in a class many years ago, everyone voted the same way, and I was so excited until I realized that everyone had voted wrong. Okay, last call.
Yeah.
Get it in.
Ask a question.
Two more people, come on. There you go. Okay, very good, very good. That is again, wave fault. Wave fault.
I know I trust you.
Good job. Let's start our study of friction with a pretest. And if I could just get some help handing these out. Thank you. Doing the help out there.
Up there.
Oh, man, I couldn't even see you too. There you go. Is anyone on the football team in this room?
I wouldn't be in this class.
I'm just gonna keep on asking that question because I need to hit someone on the forehead. You said that last time and you denied it. Is he Cosmo?
Okay.
He might be Cosmo, you don't know. Do a flip. Do a flip real quick.
Argyle and then also physics there.
Okay. Okay, are there extras?
When we went to bed, this is me now walking in.
He's one. One down here. Any extras? Anyone need one? Okay. Are there extras over here? There we go. That's what I'm talking about. Hey, raise your hand if you need one.
I like it, but I just don't want to like do it.
I started talking about this. Like,
Sorry about that. Raise your hand if you need one, okay?
It took 79.
Okay, on this pretest, people, you are pushing a wooden crate along a rough floor at constant speed in a straight line, which means constant velocity. Constant velocity. And there's a big rock sitting on top of the crate. And you need to draw the free body diagram for the crate and for the rock. And let me just remind you, when you're doing several free body diagrams, which one do you do first? Yeah, the simplest object, the thing that's touching the fewest other objects. So in this case, it would be the rock. Draw the free body diagram for the rock first and then the crate.
Yeah, like, yeah.
Oh, any force you believe is on your free body diagram, put it on there.
Don't know.
Movement. So there is a friction force. On the table on the. For the rock diagram. Is it by and on? Acceleration.
Yeah, there's only one side to this pretest. Don't turn the page over. We're gonna do that problem on the back later in the lecture.
All right, let's start. Fire on it.
That is like.
It's staying on this, like, if we had.
Diagram screening them.
How do I get this?
What should it screen?
That's all done where you work. And it share everything.
That way.
It doesn't much get better.
Okay, I understand that not everyone has had a chance to finish that, and that's okay. What I needed is for you to think about it. You can finish it on your own time, okay? Just need to think about it, so that we can use the ideas there to, talk about friction. We already know something about friction. We talked about it when we introduced the idea of, forces. It turns out that it always acts parallel to the surface of contact, the surface between the pusher and the pushee. always 90 degrees to the normal force. And it turns out it comes in two flavors, static and kinetic, or as I like to call them, difficult and easy. Okay, the static friction, that's one of the hardest, one of the most confusing of the forces. The kinetic is just way simpler than we have any right to expect. Very, very easy. Now, static is when there's no relative motion between the two objects. If I push on this and it doesn't go anywhere, that's a static friction. Kinetic friction is the type of friction you can hear. You can hear the scraping. Well, you can, I can. And that's a sure sign that you've got kinetic friction going on there. So let's talk about kinetic friction. If I were to, oh, big old sliver. Yeah. Okay, if I were to slide this, the friction causes it to stop. Okay, now what should that friction, the size of that force, depend on? Clearly not, it's not the color of the sled. What might it actually depend on? Brave soul, raise your hand. What might it depend on? The what? Yeah, what kind of materials do I have? Hockey puck on ice, or is it sandpaper on wood? What else might it depend on?
Acceleration.
The what?
Acceleration.
Acceleration. Okay, what else might it depend on? The weight. What else might it depend on?
The surface area.
The surface area. What else might it depend on?
The types of surfaces.
The
Like the type of surface. What
the
they're.
type of surface. Yeah. How rough they are.
How hard it's pushed.
How hard I push to get it going. I would expect all of these things to play a role. And yet it turns out that nature is so much simpler than, as I said, we have any right to expect. This force, this friction force, depends on two things. The types of surfaces that are in contact with each other, how rough they are, and the normal force between them. And that's it. Now, many, many years ago, 25 years ago, my wife decided that she wanted to take my class just for fun. She was a nurse. She just wanted to see what I was teaching in my physics class. And so she sat in the class. And we never told the students that she was my wife. She wasn't getting a grade. And then things went bad. My wife and I had taken ballroom dance lessons for like 15 years. We loved to dance. And we had gone to this formal dance out at this big fancy hotel. And we were just waltzing away, having a great time. And every time we'd spin around, there was one of the students from my class. And I thought, oh, this is looking bad. This is looking bad. So the next day, we're talking about friction. And I make the point that it only depends on these two things. My wife's hand goes up and I think, oh, this cannot be good. He asked me hard questions. And she said, Professor, if what you say is true, why is it that when I file down the wheels on my son's Pinewood Derby car, it wins if the surface area doesn't matter? Now, I know what the answer is. The answer has to do with rotational inertia that we're going to talk about in about 3 weeks, but I don't want to go there. And so instead I say, well, that would be my son's Pinewood Derby car too. Class, I have a confession to make. I'm sleeping with a student in the class. But she is the mother of our 4 children, and we've been married for 30 years. Now it's 46 years, so we've been married. Anyway. Let's talk about surface area. I think surface area should matter. Okay. I think that when I'm pushing that book this way, there's just more nooks and crannies that could grab on as it goes. Whereas if I push it this way, there's fewer nooks and crannies. Now, if I asked you if I could push on your arm with just a pound, would that be okay? Okay. What if I came towards you with a long hypodermic needle? Would that be okay? Yeah, not so much. It's still a pound, same force. The difference is the pressure. When I use my hand, that force is spread over a big area. When I use a needle, it's concentrated at a point. The same idea goes with friction. When I slide the book this way, there's lots of nooks and crannies, but the pressure is smaller, pushing the nooks and crannies into each other. On the other hand, when I slide it this way, fewer nooks and crannies, but now the pressure is greater, pushing those nooks and crannies into each other. And it just so happens, lucky us or blessed us, those two cancel out. So we never have to worry about the surface area. Okay? Now, we're going to talk about measuring friction. If friction is all these nooks and crannies of the book grabbing on the nooks and crannies of the table, how do you measure that? It seems like there would be so many microscopic little additions to that force. Well, we had this pretest where everything moves at constant velocity. When you see the words constant velocity, immediately replace that with zero acceleration. Balance, okay? So let's compare the horizontal forces on the crate. And for simplicity, let's get rid of that rock. We'll bring it back in just a little bit. But for now, let's just forget about the rock. If I look at the horizontal forces on the crate, I have my push on the crate and the friction force by the floor on the crate. And I made the blue one bigger than the red one because it's moving to the right. I'll wait. Gonna call me a liar? Yes. Yes. It's got to be exactly the same. If I have zero acceleration, I don't care what the velocity is. If I have zero acceleration, that diagram has to scream balance. And that means the push by Greg has to be exactly the same as the friction force that I'm trying to measure. Oh, I didn't say we were getting it moving. When I'm getting it moving from rest, I have to push harder than the friction. But once I get up to speed, once I'm going my final velocity of 3 miles an hour, I just push with the same force as the friction. Okay? Now, that gives me a way of measuring that very difficult friction force. I just put a bathroom scale between my hands and the crate. I look right on that bathroom scale to see how hard I'm pushing, and that measures the friction force. Okay? Now, we're going to do a little demonstration here. And I've got this sled, and I am wondering whether, would you help me out? Come on down. Christian, would you help me out?
Sure.
Is it Christian?
Eli.
What?
Eli.
Eli. Oh, where's Christian's over there? I'm sorry.
Get up here, man.
Oh, okay, Christian, come on down. You too, Eli. Come on up here. Okay. Now, what we're going to do is, what's your name? Jessica's going to get on the sled, and Eli and Christian are going to stand on either side of her and take her hands and make sure that she doesn't fall down. And I'm going to pull her at constant velocity across the floor, and this scale is going to tell us how hard I have to pull. Now, folks, I don't want you to be watching while we're speeding up. I want you to be watching once we get at constant velocity. So everyone close your eyes until I say you can open them. You two gentlemen, keep your eyes open because you got to keep Jessica alive here. Okay. Okay, now you can open. Okay. Okay. And that was, looks like about 56 pounds. Okay, let's go back here. And this time Eli's on there. And Jessica and Christian are going to keep him alive. I'm not sure who's going to keep me alive. Okay, grab him. Okay, close your eyes, people. Close your eyes. Oh my goodness gracious. Okay, you can open them. Okay, let's give him a hand, folks. Okay, that was up at 75 pounds. Now, let's talk about what we just did there. By putting different people on that sled, we were changing the normal force between the bottom of the sled and the floor, okay? And if we were to plot the tension in the cable as measured by that spring scale against the normal force, what we would find is that we would get, if we put different people from the class on that sled, lighter people, heavier people, we would find that we would get a straight line graph, a straight line graph. And every time we get a straight line graph in science, we're interested in the slope of that. Now, wait a minute, Greg, I thought we were talking about friction. Well, as long as I'm pulling the sled at constant velocity, the tension in the cable is the same as the friction force, is it not? So indirectly, I'm measuring the friction force. And what we find is that friction force is linearly dependent, it's proportional to the normal force, okay? Now, what if I had pulled at a much higher velocity? Well, what we find is that as long as it's zero acceleration, I'm just going to get exactly, the pull is going to be exactly the same as the friction force. And what we find experimentally is that that friction force doesn't depend on velocity. Now, folks, that's for reasonable velocities. Okay, you know that with a drag car, you spin up the wheels really fast, and that makes them stick better to the surface of the road. Well, that's because you're heating them up to where they get all melty and you're changing the wheels. Let's not go there. As long as you're going at reasonable speeds, the friction doesn't depend on velocity. Air resistance, however, depends very strongly on velocity. That's different. Okay, so it does not depend on the speed. Now, because this is a straight line graph, we can write this as the friction, the y-axis, is equal to a constant times the normal force, the horizontal axis. And that constant I'm going to write as a mu, the Greek letter m, mu. It's called the coefficient of kinetic friction. We'll talk more about that in a moment. But let's see what that mu means at a gut level. Suppose I cover the bottom of that sled with sandpaper. What's that going to do to my graph? Am I going to get this graph or this graph? Talk to your neighbor. Which one is it going to be if I had sandpaper on the...
So it's going to be.
Okay. So if this normal force here would be Jessica on the sled, you would think that with having sandpaper on the bottom of the sled, I would have a bigger friction. So that means with sandpaper, I would have this line here. And we know that this constant is the slope of the line. And so here I would have a small constant, a small coefficient, and here I would have a large coefficient. And that gives us a feeling for what the coefficient means. It's the roughness. It's how hard it is to scrape these two surfaces against each other. It's the nooks and crannies, Okay. Now, that coefficient of kinetic friction, we use the symbol mu sub k. The k is there because later we're going to need to put an s there. It represents the roughness of the surfaces, and it must be measured or tabulated for any pair of surfaces. That means there is no supercomputer in the universe powerful enough to compute, to calculate a coefficient of kinetic friction. Some poor engineer has to measure it for every two surfaces, hockey puck on ice, and then sandpaper on wood, and then this kind of sandpaper on this kind of wood. And they're big, huge volumes filled with these coefficients. Ah, yes, or you will be asked to figure it out from the information that's given, but you'll never have to look it up in a table. And it's just a pure number, okay? If I look at that formula, the friction is equal to the coefficient times the normal force. Well, friction is in newtons and the normal force is in newtons. So the coefficient is just a number. It has no unit. And some people, not us, believe that that coefficient has to be between 0 and 1. That is not true. If you have some super glue involved, that coefficient can be as big as you want it to be, okay? But it does have to be bigger than 0. Now, I've got that block sitting on that surface. Is the normal force equal to the weight? Yes or no? Shout it out. Yeah. Okay. Yeah. But what about now? If I tip that surface, is the normal force equal to the weight? No. Okay. And I can show you that that's the case. Now, folks, there are going to be problems on the next midterm that involve ramps or hills. And those problems involving ramps or hills are incredibly difficult. They involve solving two equations and two unknowns, unless you look at the problem just right. So let me show you how you look at that problem just right. Okay. What I want to do is I'm going to draw my free body diagram. I put the weight down. I put the normal up by the incline. If it's moving down the incline at constant velocity, there must be a friction force. If I tip my head so that my coordinate system lines up with my ramp or hill, so that the x component, the x-axis lines up with the hill, all of my forces line up with my coordinate system. They're either in the x direction or the y direction, except one. And it's always the same one. It's always the weight force that points towards the center of the earth. And so the way that we break up that weight force, I've seen a million different ways to do it over the years. But there's only one way that I like to call the right way, okay? So you learn the right way and you'll never get the problem wrong. What you want to do is look in the direction of the normal force by the hill or incline and go the other way. Go the other way until you can make a 90-degree turn and get to the end of the weight. And if you do that and break that up, this will be the y part of the weight and the x part of the weight. If you do that, then this angle of the hill is always going to be the same as this angle between the y part of the weight and the total weight. Okay? And now, once we've broken up that total weight into its components, its x and its y parts, we throw away the original and we use the parts. Now, if this is going down at constant velocity, that means 0 acceleration. That means this has to be balanced in both the X direction and the Y direction. In the Y direction, that means this normal force is only equal to the Y part of the weight. And this friction force is only equal to the X part of the weight. Now, folks, this is why in the Alps, in the mountains, your chalet, your cabin has a very steep roof. Okay, the steeper that roof, the smaller that normal force is. The smaller that normal force is, the smaller the friction is going to be between the snow and your roof. And that means it's going to slide off your roof before it crushes your roof as the snow gets deeper and deeper. Does that make sense? Okay. So in this case, the weight is going to be greater than the normal force. Sam's here. Everyone, let's give Sam a hand. Sam personally graded 200 exams last night. But he also ate 3 pizzas, so I don't know how it does it. Okay. You're going to have several problems like this one here. Indeed, one of your problems is almost identical to this problem. You've got a skier coming down a incline of 37 degrees. Her mass is 70 kilograms, and the coefficient of kinetic friction between the skis and the snow is 0.1. And we want to know, what is her acceleration? We know the direction of the acceleration. That's what we know, mass and use of K. We know the direction of the acceleration. It's down the ramp if she's speeding up. But how big is it? How big is it? Well, the first thing we do is we draw a free body diagram. The first force we put on the diagram is the earth pulling on the skier with a gravitational force. We then ask what touches the skier, the snow. Does it push or does it pull? It pushes. Whenever one thing pushes on another, we always have a normal force. We also have a friction force. I know that because I'm given the coefficient of kinetic friction. Now again, this problem is terribly, terribly hard unless I tip my head and use this coordinate system like that. If I tip my coordinate system, this force and this force are lined up with the coordinate system. I just have to break down the weight force. Again, I do that by looking in the direction of the normal force by the hill and going the other way until I can make a 90-degree turn. There's the 90 degrees, and get to the end of the weight. That's going to give me my X part of the weight that's lined up with this axis, my Y part of the weight that's lined up with the negative Y axis. Now the question is, which of these angles, this one or this one, is going to be 37 degrees? Now the way you remember that, the way I remember that, is by driving a spike. Okay, which angle is 37 degrees? If I drive a spike through that board, that spike always has to be perpendicular to the board. And then if I hang a plumb bob is just a mass on a string, it always hangs straight down. If I incline that board by a small angle, I'm pulling the spike away from vertical, but the plumb bob stays straight down. And I keep on doing that, and these two angles get bigger, but I'm assured that this angle between the horizontal and the board is always going to be this angle between the spike and the plumb bob. Well, what does that have to do with our skier? Well, the plumb bob is the true weight, the gravitational force that always points straight down to the center of the earth. Okay? The spike represents the Y part of the weight right there. So that's going to be my Y part of the weight. That's going to be the total weight. And so that tells me that my 37 degrees is going to be right here. There's the plumb bob. There's the spike. See if your neighbor's on the bus. Do a buddy check.
But what is that?
I understand.
All normal force is just equal to this part of the way. So hypotenuse is always the part of the triangle.
Yeah, don't get it hurt.
Why?
Okay,
Yes.
once we have broken the weight force up into its parts, we throw away the original and use the parts. Well, if we use some trig, this is going to be 700 times the cosine of 37 degrees, and this is going to be 700 times the sine of 37 degrees. And that's where I got these numbers, okay? This is equal to 3 times 140, 4 times 140, 5 times 140. This is a 3, 4, 5 triangle. Now, I throw away the original and use those parts. Because the acceleration is all in the x direction, in the y direction, I should have balance. That means this force in the positive y direction should balance this force in the negative y direction. And that means my normal force has to be 560 newtons. Does everyone see that, where we got that? Now, to find the friction force, I just take the coefficient, which is given in the problem, 0.1, and I multiply it by the normal force, which we just found is 560. Multiplying by 0.1 is the same as dividing by 10. And you can do that without your calculator. 560 divided by 10 is just 56. Does everyone see where I got the 56? Okay. Now we can use Newton's second law in the x direction. In the x direction, F net is just add up all the forces, but add them as vectors. I've got 420 down the ramp in the positive x direction. I have 56 newtons up the ramp in the negative x direction. And that's equal to the mass of 70 kilograms times the acceleration. When I solve that for acceleration, I get 5.2 meters per second squared. And that's less than 9.8, which is the goal of skiing. Okay, regardless of what your friends have told you, you want to keep your acceleration smaller than 9.8. Okay.
Why did we find the friction in the y direction, not the x direction?
Well, sorry.
Why did we find the friction with the y?
Oh, we found that the friction depends on how tightly the surfaces are pressed together. That's how the nicks and crannies interact. Okay. We're going to move on. Let's talk about the difficult friction, the static friction. If I had some sort of block here, and I were to pull with a spring scale such that the reading on the spring scale was 2 newtons, and it's not moving, it's not going anywhere. If I drew my free body diagram for that ugly block, I would have the weight down, I would have the pull by the spring scale, I would have the force of the table, the normal force by the table up, and I would have the static friction that is keeping it from moving. I'll wait, I'm a patient man. Anyone going to call me out on that? What's that block doing, people? It's accelerating out the open door. That's spooky. That's Halloween stuff, okay? No, that friction force has to be exactly 2 newtons, if that is exactly 2 newtons, okay? By Newton's second law with 0 acceleration. Now, if instead I had pulled with 4 newtons and it didn't go anywhere, still not moving, now my free body diagram is going to look like this. Well, is that static friction 2 newtons or 4 newtons? Yes. Okay, yes. And if I were to pull with 16 newtons and it's still not moving, the friction is 16 newtons. Okay, it can be 2, it can be 4, it can be 16, it can be 15.3. Okay, and yet you're able to predict how big it is. But you're not using a friction formula. What are you using? What are you using to figure out how big that friction force is? Newton's second law. Newton's second law with zero acceleration. And that's the way we usually find a static friction force. Now, what if I pull with 16.01 newtons and the surfaces break free? It moves, it takes off, and so it has an acceleration to the left. What I know is 2 things. If it's accelerating to the left, now that friction force is going to be less than the 16 newtons. And I also know that it's no longer static friction. It's the easy kind of friction that always obeys this simple equation. Okay. Now, that's the big idea, is that this static friction adjusts to the demands. If everyone takes their fingers and interlocks them, okay, these fingers represent the nooks and crannies of the bottom of that block. These fingers represent the nooks and crannies of the table. And this is the rope, okay? And the harder I pull on that rope, the harder these nooks and crannies pull on each other. And I can pull harder and harder, but eventually I'm going to pull so hard that I essentially break the bonds between those nooks and crannies. I break off my fingers, and then I've got bloody stubs rubbing against bloody stubs. Okay, that's the kinetic friction. When I've got those chemical bonds between the nooks and crannies, that's the static friction, and it can be whatever it needs to be to hold them together up to a point. And once I break free, then it's the kinetic friction. Now, static friction adjusts to the demands. We typically use Newton's second law to find the value of the static friction. And the maximum value of static friction depends on the surfaces involved and the normal force between them. We find that the maximum friction force is given by this formula here, which looks like the old formula, except we have a new coefficient between every 2 surfaces. This would be the coefficient of static friction. Now, people, listen to me if you hear nothing else. This is not the formula for static friction. This will be on the front page of your next midterm, but it is not a formula for static friction. It is a formula for the maximum value of static friction, the value at which you're breaking free. 99% of the time, you will ignore this equation. 99% of the time, you're nowhere close to breaking free of those surfaces. And so 99% of the time, you're using Newton's second law to figure out the size of the static friction. So quick clicker question. What kind of friction is desired between your car tires and the road, assuming dry conditions? Do we want kinetic, static, or both?
Thank you.
Okay. Get your vote in. There were 305 of us, but the 2 soldiers left, so 303 is what I'm looking for. Come on, baby, come on, come on, come on. 4 more people. Can't wait. Okay, we said both. And if this were a democracy, that would be true, but it's not. When you are going down the road, you do not want your wheels to be screeching unless you are a 16-year-old male. That means you want the rubber on the bottom of the wheel to be firmly meshed with the nooks and crannies of the road. And so that means what we want is static friction. Now, these are wheels of a sort, and you can see that the ridges here are firmly embedded in the mud down here. There's no relative motion there. There's no scraping going on. And so what we want is static friction. Now, here's a summary. Static friction can be anywhere in a range from 0 up to this maximum value. But kinetic friction can only be this one value given by this simple equation. Now, folks, when you get stuck in a ditch in the winter in an icy situation, how do you get out? Okay, you put your car in first gear and floor it? No, that's what the Californians do. That's silly. You're stuck there forever. Okay, in that case, your wheels are spinning and you've got this kind of friction, the kinetic friction. What you do instead is you put it in second gear and you push on the pedal, the gas just a little bit, a little bit, a little bit. What you're doing is moving that static friction between the bottom of your wheel and the ice up and up and up and up. You want to be careful not to go past this maximum, because as soon as you go past that maximum, your wheels spin and then you're stuck with that. Okay? See if your neighbor's from California. See if they've just been offended.
I'm not familiar with this stuff, but
The wheels, because the wheel is spinning.
Okay. If you turn that page over that I gave you, you'll find this sample exam problem. And given the time that we have left, we're going to work this together. Okay. The friction force exerted by the floor on block A. I want everyone to choose E here to get your points. Okay. Close enough. Okay. Trouble with authority. I love you people. Those are the ones to invite to the party. Okay, let's draw a free body diagram. We're told that the mass of the block is 25 kilograms. That means the weight force is going to be 250 Newton. And we're told that we're pulling such that the acceleration of the block is 2 meters per second squared, and that the coefficient of kinetic friction between the floor and the block is 0.3. I have the tension by the rope. I have the normal by the floor, and that's going to be 250 because there's no acceleration up or down. And I have this friction force. But it's the easy kind of friction that I can hear with my ear, the kinetic friction. And it follows this formula, 0.3 times 250. And that gives me 75. That's why that's the correct answer. Now, what about that tension force? Well, the tension force is going to be 75 Newton. How do I know? Oh, no, that was, that was the friction force. My bad. What's the tension gonna be? Well, let's look, okay? I want this diagram to screen to the right, and I want it to screen to the right by this much. Newton's second law says 25 kilograms accelerating at 2 meters per second. I need a net force or a scream of 50 newtons. Well, what's 50 newtons bigger than 75? 125. And so that's going to be the answer to part B. I was hurrying so that we could get part C. Okay. We put this smaller block, 10 kilograms, on top of the larger block. We pull with the rope so that it still has an acceleration of 2 meters per second squared. That means we're pulling harder than we were before, bigger than 125 newtons. If the coefficient of static friction between these two blocks is 0.8, we want to find how big that static friction is. Now, the first thing we need to do is draw a free body diagram for that block B. Well, I have weight down, I have normal by A and B up, and I have the friction by A on B to the right. And I know that's to the right because this diagram has to scream this acceleration. But the question is, how big is that friction force? We're going to have one last clicker question. With your clicker, let me get you started. Okay, now you can click.
Not as if this question was like 5, you look at the 5. The question is.
So to keep it up.
Okay, get your vote in. We have 3 more minutes and you're paying me for those 3 minutes, so let's make advantage of them. Last call. Okay, we are in disagreement there, but it seems like the majority of us say 80, and that's not right. The correct answer is 20, people. 20.
Yes.
Now, the people that chose 80 were using this formula for static friction. But that is not a formula for static friction. I repeat, that is not a formula for static friction. That's a formula for the maximum value of static friction. And that block B is nowhere close to slipping off the back of block A. What we use is Newton's second law. This diagram has to screen to the right by 20 newtons. 10 kilograms accelerating at 2 meters per second squared, 20 newtons. And folks, don't let me fool you like that on the next midterm. Let's get fooled in class, not on the midterm. Have a good weekend, folks.